In a prior video, we have introduced the concepts of ionic and covalent bonding. We have said that an ionic bond is formed by the transfer of electrons between two species to generate ions that establish electrostatic interactions. And then the covalent bond is simply the sharing of electrons between two atoms that forms a stabilizing interaction. Now, we can talk about intermediate cases between covalent and ionic bonds, which are actually quite frequent in nature. For example, think about the bond in HF, okay, hydrofluoric acid in the gas phase. What we actually know from experiment is that those two species are not fully separated ions, right? So this is not a perfect electrostatic attraction between a fluoride -1 ion and a proton H+. However, this is not a perfectly covalent bond either, because the electrons of this bond are not equally shared between the two atoms. The reason that we know that the electrons are not equally shared between the two atoms is because this molecule is polar. Okay? What we actually know is that at the end of the molecule where the fluorine atom is has a partial negative charge, and then the end of the molecule where the hydrogen atom is has a partial positive charge. Right? So the reason that this you have that separation of charge, which is partial but not fully ionic, is that the two electrons that are being shared by these two atoms are actually differently attracted by the fluorine and the hydrogen atom. Since the fluorine atom has a negative charge, that means that fluorine somehow is able to attract the electrons in the bond a little bit more strongly than hydrogen is. Right? So that excess of electrons around the fluorine atom confers a partial negative charge, and then the positive charge in the hydrogen atom is because that hydrogen atom is actually attracting fewer electrons than it had before. Okay? All right, so when you have this is what we call a polar covalent bond. We can actually then try to understand what the origin of the interaction between these two atoms would be. Okay, it's a polar covalent bond, which means that you actually have both covalent contributions and also ionic contribution. Okay, there is a covalent contribution because again there's here are two electrons that are in between these two atoms, which are simultaneously attracted by the fluorine and the hydrogen atom. Right, so that simultaneous attraction is what is the glue that holds that molecule together in a covalent fashion. However, in addition to that, what we actually have is now there's a negative end and a positive end, so you're going to have also an electrostatic contribution, much as what happens in a purely ionic bond through Coulomb's law. Okay, so again, in this polar covalent bond, you can have both a covalent stabilization and also an ionic attraction. Now the question is, how do we determine what are the atoms that have larger attractions to the electrons of a bond, and which atoms do not attract those covalent bond electrons so tightly? Well, this can be quantified by the concept of electronegativity, which was devised by Pauling. Okay? It turns out that there's an arbitrary formula that Pauling came up to calculate values of electronegativities for atoms in the periodic table. We're not going to study that formula in detail. Instead, we're actually going to just see the trend, and then we will see what that means in terms of polar covalent bonds across the periodic table. Right? So if you have a periodic table, which will look like this. Okay, here you have hydrogen, there you have helium. Okay, and here you will have the D blocks and the F blocks. The electronegativity increases in this fashion. Okay, so it will grow from the bottom to the top in a group, and it will grow from the left to the right in a period. Okay, so the most electronegative atom in the entire periodic table will be fluorine, and the least electronegative ion in the periodic table will be francium and then cesium. Okay, the Pauling electronegativity values would be 4.0 for fluorine, and then for cesium and francium will be 0.7 and 0.7 as well. Okay, for example, lithium, which is up here, has a value of electronegativity of 1.0, and then the hydrogen atom, just for reference, okay, has an electronegative value of 2.1. Okay? Right, so what we get from this table is that we'll notice that fluorine and hydrogen, when they form the HF bond, okay, fluorine is more electronegativity than hydrogen, okay, and what that means is that the electrons of that bond will be pulled more tightly towards the fluorine end, and that gives this pole of the molecule a slightly negative charge, a partial negative charge. Okay? Now, we can also understand that when you actually have a bond between two atoms that have exactly the same electronegativity, then you actually will not have any polar contribution at all. If we go back to the HH molecule or the FF molecule, now the atoms that form that bond, okay, have exactly the same electronegativity. And that means that no atom is pulling the electron density from the bond more tightly than the other, and you actually don't have any positive end and any negative end, right? These will be pure covalent bonds. They actually will not be polar covalent bonds. Okay? Right, so we can actually then draw a table that is going to illustrate how the type of bond that you have depends on the difference in electronegativity. Okay, so if we write here the difference in electronegativity, and then the type of bond, okay, so bond type. If we have a difference of electronegativity that is very low, okay, or zero as you have right here, then what you will have is that the bond type will be covalent. At the other side of the spectrum, if the difference in electronegativity is very high, okay, for example, like fluorine, the compound between fluorine and cesium, that will be cesium fluoride, then what will happen is that fluorine is able to pull those electrons so tightly that you actually form a full ion. Okay, so the bond is better described as simply an ionic attraction between a cesium +1 ion and a fluoride -1 ion. Okay, so there's full electron transfer there, and this is what we actually understand as an ionic bond. When you have something in the middle, okay, so we have something intermediate, this is what gives rise to the polar covalent bond, which again is kind of a hybrid between a covalent and ionic bond. Polar covalent bond. Okay, we're going to close this section on polar covalent bonds by saying that even if a bond is polar covalent and you have a tiny little separation of charges, okay, the molecule might not be fully polar. Okay, for example, let's look at the case of CO2, okay, which is this molecule. It's a linear molecule that has a double bond between carbon and oxygen, and we will explain exactly the origin of this double bond a little bit later on. But when you look at the difference in electronegativities, you actually see that oxygen happens to be more electronegative than carbon. Okay, so what will happen is that, well, the electron density of oxygen will be a little higher than in the separated atom, and then there will be a positive end in the carbon atom, right? So this bond that you have right here between this carbon atom and the oxygen atom, that is a polar covalent bond, and this bond is also a polar covalent bond. Okay, you have here the appearance of something that we call a dipole moment, which I'm going to draw as going from the positive end to the negative end, and from the positive end to the negative end. Okay, however, these dipole moments that you actually have in every one of the polar bonds cancel each other out, so that overall CO2 is actually not a polar molecule. Okay, so again, this just says that even if you have polar covalent bonds in a given molecule, okay, the overall molecule might not be polar if the dipole moments that emerge from the bond polarity in each one of the bonds, if they cancel each other out. Okay, so this video has introduced the concept of polar covalent bonds and has substantiated it with the notion of electronegativity.